Hello and welcome to another one of D's ADD videos. Today we're going to be looking at a few examples of alternating series. Again, the steps: drop the alternating part, take the limit as n approaches infinity. If the limit equals 0, move on to the next step and prove it's decreasing. But if it doesn't equal 0, then write down diverges by the nth term test, even though we started out as alternating series test. Okay, so if the limit does not equal 0. That's why I tell people when you're doing the two conditions, go ahead and do the limit first, because you might not even have to prove it's decreasing. Okay, those are the two ways to prove that it's decreasing, either the derivative or the proof. You can watch a sequence video if you need a refresher. But even though you pass the two conditions for alternating series tests, sometimes you do a test for itself, different test besides alternating series for the portion of the sequence that's not alternating, and it'll fail that test. If it fails the other test without the alternating part, then it's conditionally convergent. But if it also passes that test, it means under all conditions it was convergent, okay, not just alternating series convergence, okay? So let's look at these two problems here. The first one, the portion that makes it alternate is that negative 1 to the n in the numerator right here. So I'm going to drop it, and I'm going to look at step 1 is going to be taking the limit as n approaches infinity of 1 over n. And because it's bottom heavy, 1 over infinity is indeed 0. So we pass the first step to alternating series. Next thing is to look at a sub n of 1 over n. And you could do it two ways to prove it's decreasing. You could either do a sub n prime, would be if you brought this up as n to the negative 1, negative 1, n to the negative 2, which is negative 1 over n squared, which then at that point, when you think of the domain of the sequence is the natural numbers, which is always positive, and this 2 that I'm overemphasizing, when you square it, is also positive, whatever you plug into the end. So even if the domain wasn't negative, it still would be a positive answer. And then times this negative sign right here would make it negative. So therefore, it would be less than 0 for all n element of the natural numbers. Okay? Now, if we were to do the proof, I guess I'll do that as well. Let's compare n and n plus 1. Which one of these is greater? Well, hopefully you can see that if the domain is positive, like natural numbers are, the inequality goes like that for all n element of the natural numbers. And then if we take the reciprocal of both sides, the direction of the inequality changes. Okay, if you doubt my words, just take a couple of numbers like 2 and 3, and when we flip them, that relationship is reversed because 3 is greater than 2, but a third is smaller than a half. Okay, so therefore what we've done is we've proven it's decreasing because we've said that the original term is always greater than the next term, the n plus 1 term. Okay, so we've passed both checkpoints for AST, but we're not done. We now have to look at the series without the alternating portion and see if it still converges. Was it just a conditional convergence using alternating series, or does it always converge? Absolutely. So here you should recognize this as a p series, right? If you remember 1 over n to the p. And in this case, p equals 1. And if p is less than or equal to 1 according to the p series test, then it is divergent. So it seems like this specific problem was only convergent under the condition of AST. So that's why we would say, therefore, the original problem is conditionally convergent. And then by AST and P series. Okay? And yes, that's the big answer, but we need to write it all. Technically, you could say P series because P was equal to 1. If you guys remember, P equaling 1 has special significance. It's a harmonic P series, always divergent. Pendulum, stuff like that. Okay, so let's look at the next example. Here we have another example, but it's slightly different in the sense that the cosine term is what makes it alternate. So we can drop that and take the limit as n approaches infinity of 1 over n squared plus 1, and sure enough, that gives you 0. So we're good to go there. And then we prove it's decreasing. I'm going to do the proof on this one. It seems easier than doing chain rule. Most people don't like chain rules. So if I compare n squared plus 1 and n plus 1 squared plus 1, we know the inequality direction should be this way, right, for all an element of the natural numbers. And then if I take the reciprocal of both sides, then I have the inequality changing direction, and also for all n natural numbers. And what I've done is, again, proven that the first term is always greater than the next term, so therefore it's decreasing, which is the second condition. So now we look at just the 1 over n squared plus 1. And you could do a few tests for this one, limit comparison probably. I'm going to do integral tests just to show you that you can do integral test here. It is a positive sequence. It is continuous because there's nothing that makes that undefined. We just proved it was decreasing. Had this been an integral test by itself, then you would need to actually show work for this. But since I did the proof right up here to prove it's decreasing, I don't need to do it again. But the first two, you can just state. The third one, you got to prove. And then I take the integral from 0 to infinity of dx over x squared plus 1. That's an improper integral, so what I do is I take the limit as some constant approaches infinity, so I can make it now a defined bound. You don't want an undefined number in a defined integral. That doesn't make sense. So mathematicians have come up with a sneaky way around it using limits. And if you remember, the answer to this integral hopefully is arctangent 1 over a arctangent u over a, but the a is just 1, so it's just going to be arctangent of x evaluated between a and 0, and we take the limit as a all the way down right on each step. You get arctangent of a minus arctangent of 0. Then you end up with pi over 2 minus 0, which is pi over 2, which the integral test states that it converges if that occurs. If you get a finite answer, it converges. If you get an infinite answer, it diverges on integral test. So therefore, the whole thing is absolutely convergent. Now I'm running out of space here. by AST and integral test. So all that is part of your answer. Okay, so I guess I didn't give you an example in which the limit didn't equal 0. Let's see if I can squeeze that in here. The beauty of the digital world is about to become apparent to you right now. I can zoom in a little bit and create more space. Let's see. Let's zoom in right there. And now that tiny space is going to get much bigger. Okay, so let's look at an example. Let's look at summation n equals 1 to infinity sine of 2 pi n minus 1 over 2. And we'll do n to the 4th over n cubed plus 1. And the first step, if you remember, I'll do it in a different color. First step is going to be take the limit as n approaches infinity of the sequence without the alternating portion. And hopefully you can already see this is top heavy, it's going to equal infinity. But just to show the work, we would get infinity over infinity. That's indeterminate. You could either do L'Hopital's or factor out the n cubed. I'll just do the derivative real quick. And then we cancel. We're left with 4/3 n. If we reevaluate the limit as n approaches infinity, we're going to get infinity for our answer. So therefore, what we do, even though we started as an alternating series, you say that does not equal 0, therefore diverges by nth term. All right? I know it's kind of weird. We started out with one thing and finishing out with the other. But if you remember, this is the condition for the nth term test. You take the limit. If it equals 0, it's inconclusive. Well, but if it doesn't equal 0, it diverges. And infinity definitely doesn't equal 0. Okay? I hope I've clarified things for you. Practice, practice, practice is the most important part of this. Thank you and have a nice day.